Hi friends, my name is Parinay and my video is about multi-resolution expansion wavelets function. First of all, wavelet transforms are mathematical tools for analyzing data where features vary over different scales. For signals, features can be frequency varying over time or transient or slowly varying trends. For images, the features include edges and textures. The basic idea behind wavelet transform is that a new basis function is introduced which can be enlarged or compressed to capture both low frequencies and high frequency component of the signal. The main advantage of the wavelet is that they offer a simultaneous localization in both time and frequency domain. Wavelet transforms are very powerful compared to Fourier transforms because of its ability to describe any type of signals in both time and frequency domain simultaneously, where the Fourier transform can be described a signal from time domain to frequency domain. Here are some example pictures of wavelet transform and its first derivation of Gaussian function. And now the wavelet transform is a mathematical technique which can decompose a signal into multiple lower resolution levels by controlling the scaling and shifting factors of a single wavelet function called mother wavelet. The wavelet transform is emerging as an important processing technique in potential field methods and has contributed significantly to the processing and inversion of magnetic data. There are three major categories of wavelet applications in magnetic methods. The first is the use of natural wavelets derived from Green's function of the magnetic field to extract source parameters. A second class of methods is applied primarily for data processing that uses discrete wavelet transforms based on complexity supported orthogonal wavelets. The third category is to use discrete wavelet transforms to compress the operators and improve the numerical efficiency in equivalent sources construction and inversion of magnetic data. Now coming to the derivation of wavelet transform by taking a scaling function that meets multi-resolution analysis requirements, we can define a wavelet function with its integer translates and binary scaling spans. The difference between any two adjacent scaling can be v of I and v of I plus 1. We can define the set of wavelets. For all k belongs to z, the span of wi spaces in the figure as with the scaling function can be written also in the given way. This image shows the relation between scaling and wavelet function spaces. We can now express the spaces of all measurable square integrable functions which eliminates the scaling function and represent a function in terms of wavelets alone as given below. Wavelets would encode the difference between this approximation and the actual function. Then the below equation can be generalized to yield. And now, since the wavelet spaces resides within the spaces spanned by the next higher resolution scaling functions, any wavelet functions like its scaling function counterpart can be expressed as a weighted sum of shifted double resolution scaling functions. Then we can transform the above equation as the given equation where the call the wavelet function coefficients and it's the wavelet vector using the condition that wavelets span the orthogonal complement spaces and that integer wavelet transports are orthogonal. It can be shown that is related to by the given equation below. Here is the example wavelet with decreased scale and increased scale. And now in the by the above derivation, the Haar scaling vector was defined as the given equation using corresponding wavelet vector, and the Haar wavelet function can also be written as the given form, although the function cannot be represented accurately, but that indicates it can be expanded using an expansion function. The resulting expansion can be written as f of x is equal to fa of x plus fd of x. Thank you.